Let me start my talk. So my name is Denis Shestakov. I came from Aalto University. It's in Finland, the city of Helsinki. Okay, the talk, so I will be talking about the image similarity system done, as you may guess, with Hadoop. But to start with, let me introduce myself. So currently I'm a postdoctoral researcher at this Finnish university, and my background is essentially my PhD was about web crawling systems. So I started to work with big data sets pretty early. But my experience with Hadoop started from approximately 2009 or so. And for last 5 years or so, in most of my projects, I have been using Hadoop for different kinds of tasks. So it was processing or analyzing different kinds of data sets. And for last 2 years, I was mostly involved in this analyzing of multimedia data. Then recently, I started a path of Hadoop constructor. So essentially, I just designing, developing, and tuning Hadoop applications. So far, it's short-term projects, and they're also about multimedia data, so processing multimedia data sets with Hadoop. I'm looking for new opportunities, so feel free to talk with me directly or just drop me an email at denshe@gmail.com. All right, so let me start essentially my talk. So there will be 4 parts, so I divided my talk in 4 parts. And first 2 parts, they won't be really about Hadoop. First of all, I'll introduce to you to image search. So what is it? How does it work? You're not going to be experts after this part in image search techniques, but at least you would get very good understanding kind of the underlying things behind image search algorithms. Then perhaps the next part would be easy for you if you're familiar with MapReduce programming model. So if you're familiar, then it would be really easy for you to follow how we actually designed our system. And then in the third part and fourth part, so I'll talk about how we implemented our system using Hadoop. And then I'll concentrate a bit on specific Hadoop tools that are very useful for large joins. Because in our Hadoop workloads, basically we had this issue, and we used several features provided by the Hadoop framework. And essentially, it's so I'm going to share a bit of our experience with these tools. Then there would be the supplemental, the 5th part, which is actually kind of out of the scope, but in this project we came up with interesting trick, hack, solution, whatever you may call it. And well, I just want to share it because I think it's quite good. And then I'll simply conclude and answer your questions. All right? Okay, so firstly, I'd like to talk about image search. And of course, it's a domain in itself. It's a huge area. But perhaps for the purpose of this talk, it would be enough to just tell you that simply there are 2 ways to search within large image collection. First of all, what you can do is that you can type some words. So you provide some text. For example, you type dog, and you get these images. So these images, they contain the dog, but the images themselves, they are very different. They just contain the dog. Of course, it might be dog and some other keywords, etc. So think about Google Images. So it works in this way. And essentially, the state-of-the-art techniques is using deep learning methods to process your collection, etc. But I'm not going to cover this type of search. Instead, I'll concentrate on the so-called content-based image similarity search. So it works in the following way. If you have a large image collection, then you provide an image, query image, and then you're going to get the matches, the images that are very similar to your query image, right? So in this case, this is the picture of Rennes Cathedral in France, and well, you get all this, all the other photos of this cathedral in the collection. So in this talk, and actually in this project in our system, we dealt with content-based image similarity search. Right? What kind of applications you may think for image search? Of course, it's so-called regular image search services such as Google Images, Bing Images. There are other online services such as TinEye, etc. Then it's kind of new paradigm shift is that so far we're searching by text, but for certain search tasks, it's a good idea to search by images, right? So for instance, at eBay, they have several teams that are thinking about this. So instead of typing the name of a product, you can provide an image, and then you get the matches. So basically, specific product items, right? Then object recognition. So if you have a large image collection, or also it works with videos, because videos, in many cases, it can be converted to still images, right? So essentially, your video stream can be converted to images. For many applications, it works fine. And then you, again, apply these techniques. So you can think about applications such as face recognition, logo recognition, specific object recognition like vehicle, whatever. Then there is the huge domain, which is called computer vision. So it's robotics applications, etc. Augmented reality, think about this, virtual glasses, etc. And another two domains, these are medical imaging and astrophysics. So since I'm an academic guy, so basically in university, if you want to get an access to a really huge data set, so the best way is to go to astrophysics group and try to get an access, because these guys have huge amounts of images of night skies. All right. Okay, so again, we will talk about, so I will talk about a content-based image search. All right, so just we'll provide you with some details about how actually it works. So what's happening behind user interface. So technically you have image collection, and in most cases it's rather technical step, but quite essential. So you resize all the images to a certain size. Think about it as a normalization of your collection or something like this. There are a couple of reasons why you need to do it. One reason is that you need to control the size, and also the search quality of your system to be built also would depend on this resizing theme. Then, much more importantly, you convert your images into so-called feature description representation. Essentially, it's the whole body of research. So many people are doing the work on different feature description transformations, etc. So to put it simply, many transformations exist, and which one to choose depend on your task, application, use case. So in our work, we we used so-called sift invariant feature transformation, sift. But just to kind of summarize, if you have image, then you convert it into a set of vectors or feature descriptors. So these are highly high-dimensional vectors. In case with sift, so typically it's 128 dimensional vectors. Right? Just to better illustrate what I said on the previous slide, so we have this picture, and then on the right you can see basically the sift descriptors, sift vectors that describe this image. Actually, the numbers are bogus, so don't pay attention to them, and it's not necessarily integer numbers. It might be float, etc., depending on your implementation. But the idea is that for every image, you're going to get typically hundreds of feature descriptors. So it's one of the reasons why it's recommended to resize your images, because the smaller the image, the smaller number of descriptors you're going to get for your for each individual image in your collection. Right? So for many of you, I guess at this point, now you know what to do, right? So we converted image into a set of vectors, and we like to do image similarity search. So now you know what to do probably. So it's simply, after this, you just compare these vectors. So for every image, you have a set of vectors, and you compare these vectors with another set of vectors, right? And the point is that those images that have the closest descriptors, they are similar. So it works like this, because these feature transformations, they are designed in this way, so they have these properties. So I guess now you know how it works, okay? And then maybe some specifics, so what kind of things you may pay attention to. Right, so first of all, again, at the moment, what you can do is just for your collection of images, you convert them into this numerical vector representation, right? And then you can do the comparisons. Obviously, if you do it directly, so for your query image, the comparisons of each sifted descriptors with all the sifted descriptors of your large collection, so it's not really a good idea even for very small collection, right? Again, so approximately for image, you can think about hundreds of descriptors. So the direct comparisons are not very smart way to do it. And essentially what you can do is to simply organize the descriptors representing your collection in sort of indexed structure. So it's the same idea that works for text search. So for textual documents, you also calculate the occurrences of terms in these documents. Then you calculate different measures such as TF, IDFs, values, etc. And then you do your search. So here it's kind of the same. So basically, you just index, you cluster these descriptors of your collection. And then at the searching phase, you just search through the index collection. Obviously, it saves lots of computations, right? Okay, then so far I didn't, I talked very generally about image search, so I wasn't saying whether it's distributed version of image search or it's running on single machine. So basically, until very recently, maybe until 2 or 3 years ago, so people do essentially single server solution, so one machine, multi-threaded system that deliver this search. The problem is that this systems and techniques and algorithms, they are really poorly scalable. So you can think, so in terms of size of your image collection, so it's around 10 million images. So after this, really, you have really big performance drop, so it's just not really sustainable and working. And another problem is that this multimedia data is essentially the type of data which is really growing exponentially at the moment. So the point message here is that you need to distribute these techniques, and there are a number of approaches how you can distribute these algorithms. But quite obvious solution, at least at this summit, is to use MapReduce programming model. And let me focus on how to implement this image search using the MapReduce. To start with, here I'm going to focus even more, and since here it's important what kind of application you have in mind. So our use case was so-called copyright violation detection. So if you have a huge image data set, then time to time you'd like to check the images in your original collection on copyright violations. So the scenario is that you supply lots of images in one sitting, and then you query all these images towards your collection. So essentially it's batch querying of images. As you can see, especially if you're well familiar with MapReduce Hadoop, it's really well suited for the MapReduce programming model, right? Essentially, our queries consisted of thousands of images. Even actually, it's not just thousands; it's hundreds of thousands of images in one query. And for every image in this query batch, so the results are matching images, right? So actually, we focus on throughput, not on individual response time for every image. And we use, like I said, the sieve transformations. Here are some details about how we implemented the indexing part of our system. So first of all, we built the index tree. So it's kind of supplemental data structure that helps us do the clustering of sieved descriptors. It's actually kind of in itself, it's not really a simple thing to do. In fact, my colleagues have a full paper devoted just to this thing. And essentially, it's very important part of the system, because the good index tree is going to give you good search quality. But essentially, maybe this thing is not really belong to MapReduce, because it was just regular program that do sophisticated computation and then provides this index tree. But maybe what is more interesting is how we actually do the clustering of our sieve descriptors. So remember, we converted our original images from our collection into their sieved representations, which are simply numerical vectors. And what we do is then we do the clustering or indexing, if you like. So here I specified basically what we have as inputs for our mappers, what we have as outputs, and then the reducer output. As input, we have unsorted sieve descriptors, and also every mapper has to load this index tree. And then at the map phase, basically every SIF descriptor is checked against index tree, and depending on the particular leaf node, we determine actually the cluster to which we should put this, to which we should assign this particular SIF descriptor. Okay, so the mapper emits pairs, cluster IDs, and SIFs. Here, maybe you were able to notice is that the output of our mappers is actually is just larger than the map input, and depending on how familiar you with actual Hadoop jobs, then, well, so basically the point is that in typical Hadoop job, the map output is smaller, or very often it's much smaller than the map input. So essentially it's very untypical issue in this particular workload. And then reduces, essentially these are identity reducers, so they do nothing, but at the sorting and shuffling phases, basically all the SIFs grouped together based on their cluster IDs. Right? Then searching phase consists of two MapReduce jobs. So first of all, we need to generate so-called lookup table. So lookup table is representing query SIFs for our query batch. So in our query batch, we have lots of images. We also, so they are also converted to the SIF representations, and then we do essentially clustering and clustering or indexing of these query SIF descriptors. So we do pretty much this first thing, the first MapReduce job, right? And then we have the actual search MapReduce job that essentially do the kind of implements the image search. It's actually relatively complicated. So here mappers do quite relatively complicated things as well as reducers. But this particular MapReduce job actually is much more typical to regular MapReduce workload, because here we have, as usual, we have original map input, but the map output is much smaller. So here is, you can see some details about what mappers and reducers do. So essentially, what's happening is joining two data sets. So our original big data set containing all the SIF descriptors for our image collection, and so this data set is joined with lookup table, right? So it's joined by the cluster identifiers. Then we calculate for every matching SIFs, we calculate the KNNs, and then at the reduce phase, we do the voting. And reducers actually provide us with matches for our query batch. In a nutshell, so just if I would reformulate, just use maybe a different terminology that might be perhaps more familiar to you. So especially if you're familiar with the clustering techniques such as k-means, then you already know what we do at the indexing phase, because it's essentially it's one pass k-means over our big collection of SIF descriptors. And at the searching phase, if you're familiar with the Hadoop, so this process is called map site join. So we do joining of clustered SIFs of our original collection with SIFs at the lookup table. Then, so let me talk about kind of let me give you some Hadoop specifics. So kind of details about the Hadoop. Okay, well, so first of all, we use the standard Apache Hadoop distribution, version 1.0. And we didn't do any changes in Hadoop internals. Actually, for our algorithms, actually, it made sense to do such changes because if we would do, like I said, our indexing is essentially one pass, k-means, but if we would do several passes, k-means, then it would improve search quality. So our experience is that we tried several Hadoop distributions with supplements, for instance, for that support the iterations, etc. But our experience was really sad, so we just spent several weeks, and it didn't work because of library mismatch. So at a certain point of time, we just decided that, okay, it's going to be standard distribution. Maybe we won't be able to achieve the best performance, but at least it would be really easy for others to utilize our work and, I don't know, build on top of it. Then its technical detail is that we use, we use the machines from the French infrastructure called Grid 5000. Essentially, it's just you can build a cluster of machines for a certain period of time. And we worked a lot with 100 nodes Hadoop cluster, and also in a couple of sub-projects, I worked with a bit bigger clusters, so it was up to approximately 350 nodes. So maybe the main issue here is that the capacity and performance of these nodes, it varied. So it's specified here. So certain machines, they had 8 cores, and the third of machines, they had 24 cores. I'm talking about this 100 nodes Hadoop cluster. And also in terms of RAM, there were also significant variations. So the data set we used, so it's quite large data set, maybe not by industrial standards, but by academic standards, it's quite large. And I guess by regular standards, like common life, it's also large. So it's more than 100 million images. In terms of data size, it's here I'm talking about the size of CIF descriptors, actually. So the conversion gave us around 30 billion CIF descriptors, which resulted in approximately 4 terabytes. Also, we worked for kind of testing purposes. We worked a lot with 1 terabyte subset. And we use this data set as a destructing data set. So what does it mean? Let me explain. So basically, since we were building the image similarity system, then it's very important that we deliver good search results. So our aim, one specific goal was to deliver good search quality. So I mean such parameters as precision, recall, accuracy, etc. So we really cared about these factors. And so actually what we did is that we used our original image collection, and we added specific, another much smaller collection of images to be searched. And on top of that, for this small collection, we generated lots of variations of images in these collections. So, for example, we added, let's say, one particular image in our big collection, and for this image, we generated lots of variations. Some of these variation or distortions, they were really hard. For instance, we print the image, do crumple, and then scan it back, right? And we tried actually to find these distorted images. right? And since all these images were in our like big data set, now we can actually properly evaluate the search quality. So the search quality is completely out of the scope, but basically their results are quite good, so we were able to achieve the state-of-the-art search quality. Then here maybe more details about Hadoop workloads that we worked with. Like I said, basically this image search process is divided into two phases: image indexing and image searching, right? So the indexing workload is quite atypical. There are essentially three interesting features within this workload. First of all, it's really computational intensive. So it's not just kind of filtering your data, saying that this record is okay, this record is not. No, for every record, there are lots of computations that mapper needs to do. Then this is data-intensive workload, meaning that, like I mentioned, this issue is that the output of mappers actually is larger than the input, right? And another thing was that we have to load the large data structure into memory for every mapper in order to do the indexing. So basically for the full data set, this data structure index tree, it was quite large, so it was almost 2 gigabytes. And every mapper had to load this data structure in order to do proper indexing. So this is graphical representation, so maybe if I would skip it, so just to illustrate what I was talking about like on previous slides. So, and the searching workload, so another part of our system, it's also atypical, but at least it's much more similar to typical Hadoop job. The only atypical thing is that similar to indexing workload, with search, every mapper has to load a big data structure too. So in this case, it's lookup table. So maybe I would go to the results. So essentially, here you can see the tuning of our Hadoop cluster. So essentially, just maybe if I would summarize, so the default HDFS block sizes were not good for our workloads, so we had to increase them. Also, for indexing workload, it was obvious idea to use map output compression. Then we use JVM reuse. JVM reuse on kind of specified in the Hadoop config file. And then we do some tricking on sorting and shuffling. All right? Then with search jobs, it's just a summarization. So depending on how large our query batch was, so it took up to 80 minutes for thousands of images, like several thousands of images is approximately from 5 to 10 minutes. Since we carried on throughput, so essentially we were able to achieve such numbers as 10 milliseconds per image, but it's for very large batch, more than 200,000 images. Then what kind of features of the Hadoop we use? For spreading our data structures, index tree, and lookup tables, we use the distributed cache mechanism. Actually, I believe it's quite well known, so maybe I shouldn't go into details here. Basically, the optimization, what you can do, and like I said, here, since every mapper needs to load a big data structure, then it makes sense to increase HDFS block size. So from this point, it was quite obvious that like default block sizes, like 64 megabytes or 128, depending on distribution. So these are maybe not proper ones. Also, we use the feature provided by the standard distribution, which is called multithreaded mappers. So it works essentially is that multithreaded mapper, it spans several predefined number of threads, and each thread actually executes a map task. Right, so for our workload, it was kind of exactly what we needed. Actually, there are, at least with the current implementation that we worked with, there are downsides. So essentially, there are synchronization logs when the mappers read and write the data. So it wasn't possible to span, I don't know, like 10 threads or something like this, right? So essentially, what we came up is spanning just 2 threads, and it was quite helpful. So we were able to decrease the indexing time to approximately 30%. Then another feature that we used is called Hadoop map file. So this is less known feature, but essentially our data set was binary data that were converted into sequence files, and the map file is essentially kind of an index over your sequence files. So it actually, with map files, our experience is really positive. So it was very efficient, and essentially for relatively big batches, we were able to do really fast searches, like 2 times, and with increasing the big batch, even faster searches. Okay, then, still I have time, so I guess I'll introduce this theme. So we came up with, in my opinion, really nice hack solution. Maybe it's already known to the community, I don't know. But we worked with this Hadoop distribution 1.0. And like I mentioned, machines in our cluster, their performance varies. So the number of cores, number of memory available varies significantly. And the problem with Hadoop is that you have just one file for every node. That's why we, when configuring our cluster, we had to address the least equipped nodes. So we addressed essentially the machines with 8 cores and 24 gigabytes. And for our workloads, the memory was essential. So ideally, we would like to have different configurations for our subcluster machines, right? So what we came up is the following. So it works for the Apache Hadoop version 1.0, like I said. So essentially, you deploy your cluster, as always, with just one configuration file for every node, right? Then you create another configuration files that's addressing your subcluster machines. And then you do substitution on these kind of better equipped machines, right? And at the end, you restart task tracker. You restart task tracker on these machines. We call it smart deployment. Maybe it's already a known thing, I don't know, but it really helped us. So here's just the illustration. So it really helped. It didn't deliver kind of really huge, so it didn't really give us huge performance gains, but still it's like 15% or so, right? So, maybe to conclude, so the techniques I presented, they're actually applicable not only to images. Like I mentioned, videos for many applications, they can be considered as a set of still images. So it's applicable to videos for many tasks, I would assume. Also to audio. Again, the thing is that the trick is how you transform your audio track to a corresponding feature description. If you do it, then these techniques I was presenting, they should work. Okay. Then we did lots of analysis of Hadoop, so-called Hadoop job history logs, and at least last year there were not enough kind of available open source tools for that. So we just came up with our own in-house Perl or Python scripts. And I don't know, so if you did this analyzing of Hadoop job history logs, yeah, it would be very great for me to chat with you. Okay, there are publications, just the first one about MapReduce issues, the second one about the Hadoop issues, and kind of the third one is about application issues. Okay, so I'd like to acknowledge my colleagues. Essentially, it's my co-authors, Diana, Gilvi, and Florent. My university, the French Grid Infrastructure, Grid 5000. And that's it. Thank you very much for your attention. So, any questions?
You consider some stream processing. Like how this is possible?
So your question about streaming? Yeah, okay.
Question mainly about, do you consider some real-time algorithms for this search? Say, MapReduce is good for batch processing, but
right, okay.
Is this algorithm is applicable for some real-time search?
Not these techniques. No.
It should be other. Mm-hmm. Thank you.
Are you going to move to Hadoop 2 and maybe use Yarn feature for when you have like different server capacity?
Yeah. So this is the plan, but so far we kind of we are more interested maybe on this algorithmic thing, so like how to better adapt it to MapReduce. Yeah, but yeah, that's the plan for maybe the second half of this year. Yes.
Have you considered using min hashing for comparing the images?
So your question is about memcached?
Min hash.
Min hash?
Yes. So what you have is basically that two images that are similar get the same hash. So you just have to compare two data points directly.
No. But yeah. So like these similarity comparisons, yes, you can do it differently. Yeah, it might be kind of good way to do it too.
Can you give a little bit more detail on how you take the tags or the information out of the pictures? For how do you get the metadata of the pictures?
Actually, like for our use case, the metadata wasn't really important. So we were caring about kind of exact content-based matches. So it might be so we find, for instance, that certain region of a particular image is actually is taken and kind of, I don't know, it can be found on some website. So metadata, not really. So we so essentially kind of for the scope of this project, basically it was the only metadata we have is that the image identifiers, and that's it.
So did you do the processing on the Hadoop process?
Yeah. So it was done on Hadoop, but essentially we just implemented this sieve transformation. So it was really straightforward. Yeah.
So all the images are also stored in that process?
Yes.